All right, and now for our second talk, we're going to be having Valentino will be Valentina Peirano. I apologize if I'm making your name horribly wrong. We'll be presenting on too many screens. Sorry. We'll be presenting on the dependence of time lags upon luminosity in neutron-star low-mass X-ray binaries.
Yeah, my name is Valentina Peirano. It's fine. Sorry. So hi, I'm a PhD student at the University of Groningen, and I'm actually very excited to be giving a talk in person because I haven't given a talk in a very long time, and my PhD hasn't been very fun because of Corona. And today I'm going to talk about the latest work that we published about time lags and their dependency on luminosity in low mass X-ray binaries. So we basically base our study on neutron-star X-ray binaries, which is not really the subject that everybody is talking about here. But I will try to connect a little bit what we find in neutron stars and draw some parallels with what we've seen happening in black holes, and hopefully, I don't know, give the idea that we can, by studying neutron stars in this way, also understand what is happening in black holes. So what we're doing in this work is a timing analysis of kilohertz QPOs. And because of the talk that we just listened to, I don't have to go so much into detail about what timing analysis we do. And we focus in kilohertz QPOs, as I said, and kilohertz QPOs are basically in the higher frequency end of the power spectra coming from neutron-star X-ray binaries. They sometimes come in couples, the lower and the upper kilohertz QPO, but sometimes they also come alone, and we have to fit some model to it and try to characterize them to be able to identify them. And we focus on them because we believe that they are originated in the innermost regions of the low mass X-ray binaries, very close to the central object, either neutron-star in this, well, neutron-star in this case, but also this could be applied to black holes. And this area is, of course, very interesting to us because we want to understand what is really happening there, like what's happening with the matter that is falling into the black hole, and why we are seeing variability in the emission that is coming from this area. And well, the data we work with is basically data from the literature. In particular, we work with the analysis of Troyer et al. 2018, where they study the kilohertz QPOs on 14 different neutron-star X-ray binaries. And they look, well, here in this plot, you see they look at the lag, at the energy-dependent lag of each one of these sources, and they fitted this model. This is a linear model that they fitted to the data. And we realized that as you go down here in this figure, you can see that maybe this fit is getting a little bit flatter as we change from one source to another. And we thought that was interesting. And it not only happens in lags, but it also happens with the RMS amplitude. Here it's not as clear as the lag, but with a little bit of imagination, we can think about it. This is RMS against energy for all the sources again. And we fitted a broken line model. And the slope before the break, we think that it's also like some kind of same effect is happening when you move from one source to the other. And we were thinking which kind of property we can use to compare the lag and the RMS for different sources to try a property that will like help us describe the spectral state or the state in which the system is for each one of the sources. And we draw inspiration from the work of Mendes in 2006, where he compared the behavior of the lower kilohertz QPO, in terms of the Q factor, which is the full width maximum of the QPO divided by the central frequency of the QPO, and the RMS amplitude of the lower kilohertz QPO. And here in this plot, you see the Q max and the RMS max for the lower kilohertz QPOs, and these max values come from this plot where he plotted the Q and the RMS versus the frequency of the QPO, and found these like peak points in for each one of his sources. And he found that the Q max increases and then decreases with increasing luminosity, and the RMS remains constant up to like somehow like the same luminosity, and then decreases as well with increasing luminosity, which at the time, this was a very interesting result. And we wonder if we compare the lag with the luminosity, we'll find something similar that would tell us what's happening as the luminosity increases with the lag and the RMS amplitude of the kilohertz QPOs. So that's what we did. Here we have the slope of the lag spectrum versus the luminosity of the source for the sources that we selected for our sample. And when I say slope of the lag spectrum, I'm just talking about the slope of this fit that they did to the data in Troyer. And we found that the slope of the lag spectrum actually decreases exponentially with increasing luminosity. And not only happens in the lags, but also happens almost exactly the same with the RMS, the total RMS amplitude between 2 and 25 kilo electron volts, where also it decreases exponentially with decreasing luminosity in a very similar way, like as the lag does. So if both quantities are behaving so similarly, it makes sense to compare them to each other, right? So we also did that. We compared the slope of the lag spectrum to the total RMS amplitude, and we found that they're both correlated with each other like this, which actually suggests that there is one single property of the source that has something to do with the luminosity that is driving the way the variability changes from one source to the other. All the study we did for the lower kilohertz QPO, we also did for the upper kilohertz QPO, and we didn't find the same relationship with luminosity. And this is not surprising because before it has been said that the lower kilohertz QPO and the upper kilohertz QPO in other neutron-star Xray binaries don't behave the same, especially when we look at the lag. For example, here in 4U1728, where we see that the lag of the lower kilohertz QPO looks quite different with respect to frequency with the lag of the upper kilohertz QPO. And it's precisely this fact what allows us to draw a very simple, but I think powerful comparison with black hole X-ray binaries, because the same thing has been observed to happen for high frequency QPOs in black hole systems. In particular, I have this example of GRS 1915, where we have a high frequency QPO at 35 hertz and a high frequency QPO at 67 hertz that we can compare in the terms of the behavior of the lag with the lower and the upper kilohertz QPO respectively. So maybe this is very superficial comparison, but it really, to me, it gives an idea that something is happening here, a connection between the neutron star and the black holes, and whatever mechanism is responsible for the kilohertz QPOs in neutron stars could be responsible as well for what is happening with high frequency QPOs in black holes. But of course, as everything in science, this doesn't come without problems. We cannot just draw a comparison so simple as this. And well, sorry, here in the 67 hertz, so the one that we compare with the upper kilohertz QPO, you see that there is some kind of a dependency with energy, while the upper kilohertz QPO in many other neutron star X-ray binaries has been shown to not have any dependency with energy and remains constant. So there is some difference. We cannot just say, oh, they behave the same and it's fine. But I think it's something that is worth to take a look at and try to understand neutron stars to be able to understand black holes better as well. And well, now I'll talk a little bit briefly about the model that we think explains the lag that we see in these sources. It's I'm not an expert in this model, and because I'm not the one who worked on it, this is part of our work, our group in Groningen that works in this. But just to talk to you about what we think is happening and why we see these results. So the model is very simple. We imagine that there is a compact object in the center surrounded by a disk, and then around it it's a spherical corona. And what is happening is that we see in Compton scattering with feedback from the soft photon source that is producing this soft lag. So sometimes we will see emission coming directly from the disk towards us. Sometimes we will see this emission being reflected off the corona and then coming towards us. And sometimes we will see this emission that is being reflected from the corona, going back to the soft lag, to the soft photon source and producing a soft lag, which is what we are observing in our data. And what we think is happening is as the luminosity increases, something is changing in the way both corona and this behave with each other. We think that there is some kind of coupled oscillation between the two of them, and this is affected by the luminosity of the source, or well, not affected by the luminosity of the source, but whatever is affecting it is also affecting the luminosity of the source. So to understand this well, I show you this summary slides with all we have discovered until now in this work. We know that both the slope of the energy-dependent lag and the RMS amplitude decrease exponentially with increased luminosity, as I showed you before, and that they're both very correlated with each other. And this, together with the results before of Mendes in 2006, tell us that there is one single property of the system that is driving these changes in the variability, and that this property is somehow related with the luminosity. And we think that, yes? No,
2 minutes.
I heard something. Ah, okay, yeah, it's fine. I'm almost done. And this in the context of the model that I just presented, the Compton upscattering model with feedback from the soft photon source, suggests about this and corona and some kind of coupled oscillation. And when they reach a resonance, we see these maximum values of variability here and here. And when the luminosity increases, as I'm showing you here, the coronal contribution becomes less important because of changes in its property, maybe the size, the temperature, or the optical depth changes, for example, and the feedback fraction of photons that come back from the corona to the soft photon source decreases, making the lag and all the QPO properties less significant when the disk and the corona are not anymore in resonance. So yeah, if you are interested in any of these, I invite you to read the paper that we published this year, to also read the paper by Karpuzas in 2020, where he talks much more about the model and how it works. And if you have any questions, I'll be happy to answer. Thank you.
All right, let's thank Valentina for the first time. And I'll open it up to questions. So I'll start with questions in the room. Are there any questions in the room?
Yeah, actually, I have one question about. So I'm Pierre Petrucci. So about the resonance, what is the resonance mechanism that you need?
We imagine like a normal oscillator, I mean, it's, of course, it's not really, it doesn't work like that because they're not just normal oscillators. It's like the disk and the corona that we have no idea really how they look. But the idea is just that at some point, imagine that they're both vibrating at a certain in a certain way, and they both reach the same resonance together, amplifying the variability we see. So it works like, I don't know, like this vinyls. So imagine that the variability is just these rugs in the vinyl, and while we play the music with it, it will increase the way we see the variability. So that's why we're imagining the corona working with the disk, making the variability of the disk amplify itself when it gets reflected off the corona. That's what we mean with resonance.
Thank you.
Are there questions on Slack? There's been some talk about some of the last talk, but I apologize if I missed anything going on for this talk. And are there questions on Zoom? All right. If there's not questions on Zoom, I will ask a question. So as the RMS variability goes down, the correlation functions have a lot less to sort of grab onto, of course, to get a signal. So how robust are your measurements against finding a false lag?
A false lag? What do you mean?
Yes. Well, like, if you got some standard red noise, something like that, and you're just, basically getting the noise sort of lining up with the noise as opposed to physical lag.
Yeah, well, honestly, to answer that question, I don't know what the answer is, because basically this measurement of lags we took from the study of Troyer. Of course, we check some of the results that they did, but they did the measurements of the lags. So I don't have an answer for that, really.
No worries, no worries. Fair enough. Are there any other questions in the room?
No.
All right. Questions from Slack? I'm not seeing questions from Slack. All right. And anyone left on Zoom? Well, if not, let's thank Valentina again.